So today what I would like to do is go through these exercises just to give you some practice with the concepts, the notation and the actual physics, and if you will also the mathematics, because with these contractions I can imagine you take some practice to get this working. And I was discussing this with one of the other lecturers this morning, and one of the inherent things about general relativity is it's hard to pick up these things separately. I cannot first explain to you the notation and then do the physics and then do the mathematics. It's all this one big package deal, and well, that's just the way that it is. So I think the best way to get through this is just do a couple of exercises in full detail, both mathematics as the notation as the interpretation what the physics is. And after 2 or 3 exercises you'll get the hang of this, and you'll probably be a little bit less daunted by the complications that it looks. It's not as complicated as it looks, is what I'm saying. So, you want to do this together? Just go through this step by step?
Sure. Yep.
Part of this we already did, yes? These first exercise, I think we solved almost completely except for exercise E.
Yeah.
So I propose that we start afresh with this next exercise. It also contains the exact same exercise E, the last exercise, in which it says show that the proper velocity is normalized and such. So I propose to start afresh, exercise 2, and just go through this and see what happens. Now, before we do so, maybe it's good to have a small recap. At the end of the last lecture on Monday, I gave you a sort of step-by-step, how do you do general relativity? And it started with the idea that you have to think of the metric tensor. What this thing does is tell you how much space-time is curved. That's what this thing said. If somebody's giving you what this thing is, it's a block of 16 numbers. And if somebody has told you what these 16 numbers are, you can move on and calculate the Christoffel symbols. And this is this complicated expression in terms of derivatives of the metric tensor. So just for completeness sake, let me write down what it was. You might think, wait a minute, the last time that he wrote is he put the indices at other places. Before I think I called this one mu, and now I call it alpha. I hope you're now used to the notation enough that you understand that really doesn't matter much, right? It just gives you the same expressions. You're completely free to take a mathematical calculation, and if something is called x, you might as well call it y, as long as you do it everywhere. So that's what I'm doing here. Now, as a bit of shorthand notation, derivatives, like this, a derivative with respect to the alpha part of this number of space-time dimensions, I'm going to abbreviate by this. There's no physics here, it's just shorthand notation, so I don't have to do this thing over thing else. So just to make this notation a little bit shorter, okay? So without a derivation, because that's a big exercise that we're going to see solved on Monday if everything goes well, the idea now is that this is a combination of derivatives of metric tensor in the following way. Always have to make sure that I do it correctly myself. This should be beta mu minus plus. This then is a mu, and this then is a mu alpha minus t beta g mu. This is the same expression that I gave a couple of days ago. Again, what I used to call mu is now called alpha maybe, but apart from that, it's the same expression. Why this? Again, this is a big exercise that you will see solved on Monday.
How do you remember writing like this?
Well, having done it many, many times.
Right, just practice. Right?
Yes, this is just practice, but there's also some logic to it, which you understand if you have gone through the derivation of this formula. So, yes?
Isn't the middle one supposed to be g mu beta?
Yes, because that is the running index. So, me and my mouth full of you practice a lot and you get do everything correctly is not exactly right. You do things wrong. Yeah, you're right. The running index, the one that you do the contraction with, the one that you have one of them upstairs and downstairs in this expression is the beta. Anyway, so once you have the metric tensor, how curved space-time is, you can calculate these things. Last time I said there were, how many were there? 64 of these things or so? Right?
More.
Yeah. And that's because this mu can have 4 values, 1 time and 3 space. So 4 options for this one, 4 of this one, 4 of that one. That gives you 4 to the power 3 options, and that's 64. It's not quite as bad though. I did not mention it last time because it didn't tell you for shock effect. 64, it's less. And the reason is that if you look at this and you would replace your mu's by mu's and the other way around, you would just swap these. Notice in this expression that if you replace mu by mu here, you would just get this term. And if you would replace mu by mu in this term, you get this term. So swapping mu's and mu's doesn't change anything here. And mu's and mu's here changed also doesn't change much. Sure, this now is called mu and this one is called mu, but it will give you the same number for this piece of the metric. So what I'm saying is, in the Christoffel symbols, you're allowed to replace mu's by mu's, to swap these two around, and you will get the same number back. So that means of the 16 numbers that this constitutes, but it's so-called symmetric, you can figure out that in real life there's only 10 different ones. Times this 4 is 40, so it's really 40 of them. It's still a lot. And again, this is why we like this this notation where you contract things, that you have this Einstein summation convention, because otherwise you end up with, in principle, writing down 40 terms in all your equations. So this is much more economic. Again, this is what I said before at the beginning. This is why you cannot learn how to do general relativity without also immediately introducing the notation. Otherwise, I first have to teach you how the physics works and writing down 40 terms all the time. So it's a package deal. So, okay, back to our overview. This is the idea. Somebody gives you a curved space-time. You calculate Christoffel symbols, 40 of them, not 64. Most of them are 0, so usually it's even a smaller amount. Once you have the Christoffel symbols, you do the following. You substitute the Christoffel symbols in this equation that I'm now writing down. So-called geodesic equation. Maybe you recall why this is, and that is that things in the curved space-time tend to move in such a way that it minimizes the amount of proper time. And then this equation is exactly that thing that tells you how to minimize proper time. If your x alphas, your 4 dimensions, your 4 positions and moments in time of your moving object obey this equation, then automatically the amount of proper time is the smallest. It's built in. So that's then the next step. You have a Christoffels, you put it in here, you get 4 equations, because for every alpha you have an equation, so that's 4 in total. You have to solve all 4 of them. And what you get out is these 4 numbers, functions, of the moving thing that you're observing. X alpha is 4 functions, a time function as a function of tau, and 3 space functions as a function of tau. Once you solve this one, you get these 4 functions, and these 4 functions is exactly how things move in a curved space-time. That was the idea. So what we have here is how you calculate moving things in curved space-times. And we've built this up from the beginning, right? We never smuggled anything in. We just started with a basic postulate, equivalence principle, and such that this is what we got out. So this is very nice. Now, the devil's in the details. Solving this equation, that's the crappy part. This part is straightforward. It's elaborate because there's so many terms and such, but in principle, this you can simply do. It's just taking derivatives. Solving these 4 differential equations is very difficult. And maybe you remember from a couple of days ago that usually these 4 equations are coupled. You need the solution of the one to start finding the solution of the other. But the solution of the one depends on yet another of these functions, and all these functions depend on each other. It's called a coupled differential equation. So that makes it extremely difficult, unfortunately. So that's the idea. And that's that. This is how you do general relativity. Well, one part of it. This is the part, if you know curvature of space-time, you can calculate how things move. Still haven't told you where you get these from, but this is not for today. Alright, so that's the idea. One last comment, here's some physics. I mentioned that at the last of the last lecture, at the end of the last lecture, maybe it's good to emphasize that once more. Yes, please.
Sorry to interrupt you.
No, go ahead.
The reason why, just to be sure I'm not understanding something stupid, the reason why there are 4 expressions at the end is because of the Christopher symbol. Because, for example, here it's alpha, it could be beta, well, all the 4 dimensions.
Yes, it's because of the 4 dimensions. If something moves through space-time, then there are 4 things that he has to move through. 3 space dimensions, 1 time dimension.
And so we apply each of those 4 values into the middle expression over there.
Yes.
And we get 4 values out of that.
No, you don't get 4 values. You get 1 value or 1 function.
Okay. Why do we? Oh, per value.
Yes.
Yeah, that's.
So if for instance we have this thing moving through a curved space-time, you ask me what is its z direction at any moment in time. I say, well, take the alpha that corresponds to z, calculate the Christoffels that correspond to z. You get a number of Christoffels. Those Christoffels you put in here. You have 1 equation that tells you as its solution how z moves through space.
Okay.
And this you have to do 3 more times for the other 2 space dimensions than for the 1 time dimension. And then you have how everything moves through space. That's the idea.
Okay.
Again, we will do this in full detail in a moment for an example. Yeah, the comment that I want to make here, some physics. At the moment, we saw this before, at the moment that you are looking at something that is moving through a non-curved space-time, and you know now that a non-curved space-time means that your metric is Minkowski metric. The one that has the -1 here and the other is ones, missing 0 somewhere, but this thing, right? This is an uncurved space-time. And you remember from a couple of days ago that if you calculate Christoffels of this particular non-curved space-time, all Christoffels are going to be 0. Because you have to take derivatives of this thing, but it only consists of constants, and derivatives of constants are all 0. So you see immediately at the moment that you're in an uncurved space-time, all Christoffels are 0. That means that this whole part is 0 for all 4 equations, and then you just get Newton's first law, that things move in a straight line, constant velocity. Right? Second derivative is equal to 0 means straight line, constant velocity. So this is exactly what you would expect. Non-curved, no gravity, means things just move in straight lines. At the moment that things, that the space-time is curved, there is gravity, then you will not have constants here, you will have functions. These derivatives will not be 0, and then this looks like Newton's second law. Second derivative equals something. And from Newton's second law you know that if a second derivative of your position equals something, the thing that which it equals is a force. So you see immediately that a curved space-time gives you Christoffels, gives you a force. So curved space-time really is force. And that's the whole idea, that you can describe the force of gravity by curved space-times. It's all in here now. This is in general relativity. It works for all cases. Right. Yes.
So I think about it again. Like last time I did the comment, like when you're like in a curved space, like it's curved for someone outside of the reference, and someone who is in that specific space, it looks normal.
You have to be more specific now. What do you mean? Somebody's in the space-time looks uncurved or looks normal? What do you mean?
That's what we learned in, if I'm not mistaken, in the theory of relativity in the other course, is that when, for example, the space is curved, like because of a heavy object, a heavy gravitational object,
yes.
And from outside you see that the space is bending towards this object, and someone who is like in that specific curve, for him it looks like normal. It doesn't see the curve itself.
Yeah.
So so for that guy who is like at this specific bending, can he use the Minkowski
yes.
matrix?
Yes, you're very right. If you're in a curved space-time, but you're only one observer, and you're somewhere in a curved space-time, for you locally it will look very uncurved. This is the idea of a local inertial frame, that if you look small enough at a small time scale, then for you space-time looks uncurved. So that is true.
Okay. So for the one who is like near this massive object, he sees that the other one's reference is like curved.
Yes.
But how can he explain this? Because he can say like, oh, the other one outside of this heavy object is far away from any other heavy object. Why is his space-time curved?
Because relativity only tells you something about the difference in time scales and the difference in length scales between two observers.
Mm-hmm.
So any one observer can never say whether he's in a curved space-time or not. You always have to compare it to somebody else. And if that somebody else is extremely close to you and you're both in the same local inertial frame, both of you cannot conclude that you are curved. But if you are very far away from each other, far away that the curvature becomes apparent, then you can say, wait a minute, we're on a curved space.
Okay.
So you need two observers. Any single one observer, even extremely close to, say, a black hole or so, will not notice that he's in a curved space-time. Here's another interpretation of the word relativity. You have to compare yourself to somebody else in order to make conclusions. But you're extremely right. Even extremely curved space-time, in your local inertial frame, everything will look as if you can just use this. That's very true. And it only becomes apparent at the moment that you look from somebody far away. But here's a good example. I mean, we're on a curved space right now. Well, the space is not curved, it's the Earth that's curved. You and I, in this classroom, if we do our Euclidean measurements on triangles on the floor, we just find Euclidean geometry, yes? Mm-hmm. So our little local Euclidean frame, seems to give us the interpretation that we are not on a curved Earth. Yet if you're going to compare yourself to somebody who's standing way over there and the two of you are going to draw a triangle, then you will see that things are curved. So the main message here is if you look close enough, as in small enough scale, the curved Earth will look flat and the curved space-time will look Minkowskian. So there's that. Alright, let's put this into practice. This is exercise 2. It's still a Minkowski space-time. Another point of the last lecture, namely that you can have a space-time that its metric looks curved, but it isn't. And it's just because you have written your coordinates in that uncurved space-time in some crappy way, not crappy, but in some way that makes it look as if your space-time is not curved anymore. And this is one of these examples. So everything we're going to do is still special relativity. But that means that we already know what this is going to give us, yes? The answer to this solution. Straight lines, constant velocity. So here's a check. Let's see if that happens. The crappy coordinates that I've chosen, by crappy I mean it takes more time to calculate them. I mean there's nothing wrong with them. Sorry?
Less nice to work with.
Yes, exactly. Well, it depends on the issue, in fact, right? I mean these are spherical coordinates. And the spherical coordinates, the time coordinate is still the same. So the new coordinates, the primed coordinates, time is still time. The x coordinates, check, are cosine phi sine theta. Y is r sine phi sine theta. And finally the z is r cosine theta. And just as a reference, the idea is that here's your uncurved space. I'm not going to draw the time axis. We don't need it for this exercise. Here's a sphere. And of course any point in this uncurved space-time you can either write by saying what its x, y, z coordinates are, or you could also say, you know what, this point here is an angle theta from the z-axis. Suppose that it is here. It's an angle phi from the x-axis, and from the origin is r amount of meters in that direction. It's just another way of writing positions in an uncurved space-time. Alright. How should we do this? Somebody who wants to attempt this, or maybe write out their answer? Should I do this?
It's the writing, yes?
It's like we had like 3 pages of sine and cosine stuff.
Did you get the right answer? So
We did actually, yeah.
Only for D we didn't get there.
okay, but
For A.
the metric is what I'm asking.
Yeah, we
You found the
got
right
that.
metric,
Yes.
yeah? Because this is just an exercise in algebra, so I'm going to tell you what the steps are, how do you do this, and the rest is just you going through the algebra, which indeed in this case takes 3 pages or so. It's very trivial algebra, it's just sines and cosines, what's the derivative of a sine, it's a cosine, and all these
There's
things.
identities as well.
Yes.
Yes, and you have to square them and
Yes.
add everything together, it takes a while. So I'm going to tell you what the idea is, and if you want to know what the details were, just look at their notebook, okay? Here's the idea. Our Minkowski metric, or Minkowski line element I should say, is this one. In order to write this in terms of these new coordinates, I will have to rewrite my dt into the new coordinates. I have to write my dx in new coordinates, dy and dz, square each of them, and then do this whole sum. And then with some algebra tricks, simplify everything and hope that you get the right answer. I'm going to do this for one of them. Let's do it for the x. Okay? Then the y and the z, again, it says algebra, it's the same exercise, and then put everything together. So let's do that here. I'm just going to write my x, which is defined over there, as r cosine phi sine theta. And what I need in order to put it here is a dx. So I have to turn my x into a dx. And I hope you remember from last time how to do this. Do you? Is the question. I know that you do because you found the right answer.
Is it not cosinus phi times sinus theta?
Why would that be?
Oh. No, dr cosine.
Okay, well that's one of them. Yes.
Yeah.
You're right. Cosine phi sine theta dr. This is one, but it comes in 3 terms. This one.
Oh, it's like a triple product rule.
It's a triple product rule. This obeys making a d out of an x, a dx, just follows the rules of differentiation. So you have a product of 3 things, then you have to use a product rule for this. The product rule means take one of these things, take its d, and leave the rest as is. So you could take r, take its d, which is a dr, and leave this one as is. This is how you get this term. But the product rule also tells you that you have to add to this, that you have to take one of the others to be the thing of which you take the d, and leave the rest as is. So one of the other terms is going to be that, let's make the cosine phi the thing of which we're going to take the d, then leave the rest as is, so the r, the sine theta stay the same, and now you take the derivative of cosine phi. What is the derivative of cosine phi?
Minus sine phi times d phi.
Yes. That is correct. The derivative of cosine phi, the derivative of cosine is a minus sine. And by the chain rule, you still have to do the derivative of the thing inside the sine, which is the phi. So you get this. Last term, let's take the theta, the thing we're going to take the derivative of, and leave the rest as is. Leaving the rest as is means r cosine phi, this will stay as is. Take the derivative of d sine. What is the derivative of d sine?
Cos d phi.
Is
D
it the
theta.
cosine of d phi? Or d
No,
theta?
cos phi d phi.
Is it
Cos theta.
theta?
Ah, theta.
Yes. There you go. There it is. This is the derivative. Well, if I'm going to be very puristic for the mathematicians who might be watching, this is called a differential, another derivative. They follow the same rules, but they have a slightly different meaning, but that's beside the point for now. Okay, so we have now that we now know how to write our x as a dx. That's this whole expression. But we don't need dx, we need dx squared. Life sucks. Squared.
It's great.
Well, enjoy.
Yes, it was fun, yeah.
That was a fun exercise, wasn't it? Just for funsies, let's write this one out. This is algebra, by the way, not even derivatives. This is just writing out this stupid thing here.
You actually writing it out.
That's like the steps.
Oh,
Now all the scrappy cross terms. This one of the things we will get is, you might want to help me here, I'm just trying to do this in real time. I take this one squared, that's these two, but the two are, oh my god. What did I do to you when I gave you this exercise?
Would you recommend to first try and rearrange something with the terms with the r's and the cosines? Maybe at all.
Yeah, I think there's this law of conservation of misery here. I mean, however you try to do this, there's always a crappy step somewhere. This is one of them. What I did in my mind, or what I'm attempting to do, is first take this whole thing squared, which gives you these three terms, and then take that thing and square it with that thing. Now let's skip those steps. Can you just tell me what the answer is? This takes too long. There's no physics here.
You want to like without rearrangements or?
You've put it in here and then rearrange with the rest?
Yeah, but like we first like calculated the whole thing, like what cancelled out with dy and dz already, and then some figured entities.
Alright.
So we have a big thing.
Okay, you know what? I'm just going to immediately go to the final answer because I know it by heart. Yeah, not because I do this calculation mentally this fast, but simply because the answer is well known to me.
Shouldn't have said that.
Sorry?
Shouldn't have said that.
Yeah. Oh no, I did this mentally now, and I find that this comes out. Anyway, I hope you see that there's no mathematical and or physical difficulty here. This is just writing out, and it takes a while. Okay, and I was halfway and decided, you know, I don't want to do this today. You okay, Hans?
Well.
Oh.
Was it actually big?
I mean, I'm functional, so
Okay.
I'm not gonna throw up or.
Okay. Well, I mean, if for some reason this is not a good time for you, fully imagine it.
Pure physical.
Okay. Let's see. Well, I said I know this by heart, but I still might want to have you checking up on me. This is r, this is d5 squared minus r squared. Yeah, this is it. I think this is it, yes? Can you check?
Yeah.
Yeah,
We have a minus in front of c
We
squared.
had a minus and plus is swapped around, but that's all.
Okay.
But it's the same.
Yeah.
All the coefficients are the
Good.
same.
Okay.
Yeah.
This, again, just skipping the non-insightful algebraics.
Everything cancels out to get that.
Yes,
Okay.
yes. And imagine this, yeah, Francesco, it's terrible. When you first have to write out this,
I want to take this one.
you get this crappy expression, that's just the x. You have to do the
Or
same exercise with dy and
And
dz.
everything cancels out.
Everything
Oh,
together,
yeah, just
and
an
everything
A,
cancels
B,
out,
C.
ultimately this one here.
I believe this.
Yes, okay, well again, it's, I don't know how long it took you, but it takes a while.
Well, we did A and B, right?
Yes.
A and B took 2 hours for us.
Yeah.
so-
Okay, well. This is what you get ultimately, yeah?
But hey, didn't we have fun?
We did.
I actually did it.
Yeah. But what I was looking for is the metric, and what I have now is the line element. Again, this is the same expression, it's the same physics, just written in different coordinates, and I'm looking for the metric. And the metric you should now know very well is this expression, but now written as a contraction, and that word you should know by now as well, as this. The question is, what is this block of 16 numbers that if you would write this out, you would get this back? That's the question.
We didn't do that explicitly.
Not really.
It's not hard to figure out what this is. Should we just...
Well, you can already see that you should only consider the cases where mu and nu are equal.
Yeah.
Yes, thank
So
you.
pretty visible.
Yes,
Should be a diagonal.
yes, exactly.
Mhm.
This is the practice that you need, I guess, right? For a lot of people. This is why it's good to go through these exercises. But let's go through your argumentation. This has to be such that it equals this. That's the idea. This is how you get your G mu u, or the G alpha beta. And they correctly point out, well, I can immediately see that there's a dt squared, a dr squared, d theta squared, d phi squared. I don't have a dt with a d theta, for instance. I don't have a dr with a d phi. So that apparently, this combination, a dx of one of them and a dx of the other one, the only ones that appear in here are when these are exactly the same. dt with dt, dx, or dr with dr, d phi with d phi, d theta with d theta. There's no d theta, dt, say. And that tells you that the metric that you're looking for should give you zeros, a zero contribution for all the parts that are trying to get an alpha not equal to beta. Every time that you try to put a dt and a dr together, that should not be there. That means that in that place in the metric there should be a zero. So there's really only 4 points here where it's not zero. Namely exactly the ones where the alpha is equal to the beta, which is on the diagonal. And the question then is just, what are these things? Now, what is in front of the first coordinate here? What number is here?
C squared.
No, 1.
We have to be more careful
1,
here.
because it's, yeah.
The c
Yes.
squared is already included in
Yes,
the...
because x alpha
in the
in our new
Yes.
coordinates is c dt,
Yeah.
dx, c dt, dr, d theta, d phi, right? So again, I ask a question. C squared dt squared is already here. So what is this number here?
So 1.
It's minus 1.
Yeah, okay.
Because of this minus.
Mhm.
It should be a cancelling minus. So there's minus 1 here. How about the r? What number does it come with?
1.
Yes, it comes with a 1. There's a minus 1 here, but it cancels out against this minus here. So there should be a 1 here. Over here, what's the number in front of d theta squared?
R squared.
R squared. There's a minus r squared here, but it cancels out with this minus, so there should be an r squared here. And finally, the number here, of course, is minus r squared sine theta squared. With this minus should give you plus r squared sine theta squared. All this work, but now we have the metric tensor. Here it is. I'll put a block around it. Okay, there's that. We've just that now. We have the metric tensor and our new coordinates. Let's do some Christoffels. Wait a minute, there was 40 Christoffels in total, yes, but usually so just some clever looking, you can usually immediately tell which are zero, which are non-zero. So let's do a couple of them. I wrote them out for you. This is probably also the way they're going to ask on the exam, unless it's an extremely simple curved spacetime. A typical answer question would be calculate 2 of them and check that they are true given this metric. I'm not going to ask calculate all 40 of them, say. So let's do a couple of them. I gave you 6. It's good to go through all of them, but any preference that you would like to see?
There was one where we actually came out with something different than
Yeah,
the sheet
so
of
it's
paper,
the-
so maybe
the
we could try that one.
Was that the bottom left one?
That was the middle one of the bottom row.
Yeah, that one. So the
Gamma R theta theta?
that one. Yeah.
Okay.
Because of the
So again, on an exam, I'll typically ask you, or give you, here's a space-time cursor, here's a metric tensor, calculate the following 3 Christoffel symbols, and usually I will probably give you the rest of them. Right? All right. This is one of them that I say is non-zero. The ones that I did not list are simply 0. So it's really not that bad, right? Of the 40 that exist in principle, there's only 6 of them that are non-zero. All right, well, here's the definition again. Here's the definition. There's a G, and according, if you want the GR, or the Christoffel with the R upstairs, you need to put your alpha to be the R coordinate. The R coordinate is this one. You could call it 1. It's right 0, 1, 2, 3. So it's the 1th in your vector. I just call it R. And then there's still a beta here. And then you get this whole crappy thing that comes next. Now here's already a clever step of continuing. And that is that you need the metric tensor, but now with the indices upstairs. And Lizzie asked a question last time, well, is that the same thing as downstairs? It is not. But I told you that for all the metrics that we're going to look at, this thing is just the inverse of these numbers. Alright? Now here's a beta. Now if I go to the R row, that's this one here, I can immediately tell that the column, the beta is going to look at the columns. This column will give me 0, that will give me 0, that will give me 0. The only column that does not give 0 is the R column itself. So beta necessarily has to be R. So this is one of these little clever tricks. Immediately you can tell, I don't have to look at all the betas, I just take the R beta. Alright, now let's go on with this. My mu and my nu here are both theta, because that's the one that I'm trying to calculate here. So I'm just going to write mu and nu are going to be theta. My beta, just a second ago I said, can only be R. So I just get a number of these things. Here's mu, which is theta. G, then a beta downstairs, and beta is R. Nu is another theta. Theta R, and then I just continue like this. So this is this.
So only the last term within the brackets is going to be non-zero.
Yes. Because gr theta, look at the metric, the R row is this one and the theta column is this one. R theta is 0. So derivative of 0 just gives you 0. So this is 0, same thing here, 0. This is the only non-zero one. I get minus 1/2 GRR dr g theta theta. And now just plug in the numbers. See what happens.
Yeah.
Equals minus 1/2 GRR. What is that number?
Is this 1?
That's just 1. And if you're going to be pedantic about it, it's 1/1.
Yeah.
Right?
Oh.
Yeah.
But that's still
It has
1.
to be the inverse, right?
Yeah, it has
Yeah.
to be the inverse. Okay, so this one is just 1. I still have to take the derivative with respect to R of G theta theta.
Yes.
And what is G theta theta?
Squared.
R squared. Is this one, the theta row and the theta column.
Yeah.
Then you take the derivative and you get
Half and the 2 cancel out.
yes, so that gives us minus R.
Yeah.
Yes.
So we were at that.
Yeah.
Yeah, because
In
it's
the book it's
1 minus 1
1
over 1
over
R.
Okay.
Yeah.
Oh, no idea what happened there. And that's probably just a typo then.
Okay.
Okay, then you were right.
Yes.
But this is the answer, it's minus R. There you go. I'll correct it on the problem sheet. Okay, good. Now this was a sort of an easy exercise because now I just tell you that r theta theta, Christoffel r theta theta was non-zero. Let's do it the other way around. Let's suppose that we have no idea which ones are zero and calculate one or two of them. Right? This is a somewhat more difficult problem. If I already tell you which ones are not zero, it's just a matter of plugging in the numbers and checking what comes out. Let's do it the other way. Just as a little bit of practice. Okay, you tell me which value you're going to put here.
Theta.
Theta, sure. Okay. And then the question is, which then of the following mu nu, which mu nu are going to give me non-zero gammas, given that theta has already been chosen? Question of interpretation. I told you before that you can see this part as a force, right? Second derivative of a position with respect to time equals something force-ish. Which force am I calculating now? In what direction is this force pulling? If I'm going to do the gamma thetas.
We'll be pulling in the theta direction.
Yes.
Yeah.
Because apparently I've chosen alpha to be the theta direction. So I'm calculating here what the acceleration is in theta direction. So it's apparently the force in theta direction. The thing I'm calculating here is going to be a measure of how strongly gravity is pulling something in along this line. Here's an interpretation of what a gamma means, the Christoffel symbol.
Okay.
Right. 1/2. Okay. Maybe somebody can dictate what I should do next.
So what are we looking for? I didn't do like.
I specified my my alpha here. Yes,
Yeah.
I said it has to be the one in theta direction,
Yeah.
but I haven't specified my mu and my nu yet.
Okay.
And well, both of them come with 4 options.
But we have to choose them in such a way that.
That the gammas are not zero, because I'm not interested in zero forces. I'm interested in the ones that have a force that have a value. My question is, instead of painstakingly taking mu to have the 4 values and then nu to 4 values and then calculate doing this little step and see what comes out, maybe we can, or as we go along, figure out which ones are zero and which ones are not. That's my question here. No. You tell me, what should I do? This is also going to be an exam question, you can imagine this, yes.
So we choose alpha and theta, then also beta to be theta, right?
That is very correct. The alpha here we have chosen as theta,
Yeah.
because that's the choice that we made here. So this is one. And then you say the beta is also theta?
Yeah.
Why is that?
Because it's the only non-zero.
Exactly. We are in the theta row, which is this one. And the only one that is not zero there is when you're also in the theta column. So the only beta that works is theta. All right.
Fill that in for the rest.
Yeah, then put it in for the rest, because the mu is still there. Gamma, all the betas have now simply become thetas. I'm just going to copy this one and replace all my betas by thetas. Mu theta minus theta. All right.
Isn't that a plus?
There is a plus. Yes. All right. Well, that's a good comment. We've already got rid of many options now, just by realizing that this is diagonal. That the only ones that work if these two numbers are the same. So that's good. We've made a good step now. Next, we still haven't figured out which mu and u to take in order to get something and not get zero.
Well, one thing is the derivatives that are in there. They need to be like the variables with respect to which you're going to derive.
Yes.
Have to correspond with variables that actually turn up in the metric, right?
Yes.
Yeah. That's
Because otherwise,
otherwise
exactly.
it's going to be zero.
Yes.
So you need to use r and theta in this case.
Yes, that's very good. All the thingies in your metric tensor at most depend on r or theta or both, but they do not depend on time, they also do not depend on phi. So that means there's no point in trying to make mu a t or a phi, because those derivatives do not exist anywhere. So I can immediately tell that in order for this one to give me non-zero, mu should not be t or phi.
Yeah.
Here, the same thing. In order for this one not to be zero, that means mu is not allowed to be t or phi. Here, I can also say something, because I have to take the theta derivative of the metric. Now, which is the only one for which that gives us something?
Phi.
Phi, or phi.
Phi.
Yeah.
So you can immediately tell, well, I know at least one of them that's going to give me non-zero, and that is when mu and mu are phi. So let's try that one.
But you can say the same thing if you put mu to r and v to theta.
Yes, that's true. So that's another option. So
Okay.
it's going to go logically through the options.
How many options?
Usually you're very quickly done.
Okay.
But you're right. So let's take that one as the second one. But here's one. I mean, the only way that this thing will not give me zero is when mu and u are both phi, because that's the only theta dependent part of the metric. So apparently I can immediately tell, well, this one is certainly not going to give me zero.
Yeah.
So let's see what it does give us. Well, it's 1/2 g theta theta. Note mu and u I've both made phi now. So all mu's and u's are going to be replaced by phi's. There you go. This one will not be zero, yes? This is why we chose mu and u as phi's. So this one will not be zero. How about these?
There is no phi's in the metric, so those derivatives will just give
Yes.
zero.
Exactly. It's even worse than that. It's not just that these things will not depend on phi, so the derivative will be zero.
And the elements themselves are also
They are themselves zero to begin with. So these are super zero.
super
So,
zero.
yeah. Don't use that on any official exams, okay?
Oh, I'm so gonna do that.
I'm grading it, so I make this comment now. So, all right. So apparently, gamma with a theta upstairs and two phi's downstairs is this expression, and it's not zero. And what it is, we're going to find out by just doing the derivatives now. Well, let's see what it is. Minus 1/2 g theta theta upstairs. What is that number?
1 over r squared.
1 over r squared, exactly. Then I have to take the derivative with respect to theta of g phi phi, but now the phi's are downstairs. So, of what do I take the derivative?
R squared sine theta squared.
Yes.
Oh look, it cancels out.
Something will cancel out, that's true. Not everything though. So there's that. And the rest is just doing your first year derivative taking. D theta will not feel the r squared, right? So the r squared is a constant as far as the theta is concerned, because in front of the derivative cancels out the 1 over r squared. So we get 1 minus 1/2 times the theta derivative of sine squared theta. What is that number?
2 sinus theta times cosinus
Yes.
theta times d theta.
No d theta.
No?
That's
Oh.
in case of differentials. This
Oh,
is
okay.
derivative.
Okay.
I told you there's a subtle difference.
Mhm.
This is one of them. Now the 2's cancel out again. And ultimately I get minus sine theta cosine theta. And I think that's one of the ones that I listed.
Yep.
Well, it should be,
Yes.
because you listed all the ones that are not zero.
Yes.
Yeah.
But then again, I'm prone to make mistakes, right? Like the one over
Yeah.
just a second ago, so it's good to check. So, we found one of them that is non-zero, just by some clever looking, instead of going through all the 40 combinations. Let's do one more. Francesco, you had an idea of
Yeah.
how to turn this one into...
Put mu r
Oh yeah, okay, let's do that.
and V was theta.
Yeah, it's a new, but it's my crappy handwriting. It's the
Oh.
Greek letter N, but not sure. This is convention notation that if you go to look at space-time coordinates, they're always written in Greek letters. So, anyway, so you said, can you repeat?
The Greek letter V, theta, and mu r.
Okay, so this
This
one
R.
R,
Yeah.
make that one theta.
Yeah.
Okay, because then you have g theta theta, which is this one, which has an r derivative, so you have to take mu to be r. So apparently, just by looking cleverly, you can tell that one of the ones that is not going to be 0 is when mu is r and u is theta. So the r theta one is certain to not give us 0. And the rest is just, again, now putting everything in, see what happens. -1/2 g theta theta, then the first term becomes r g theta theta, by construction, we chose it this way, plus then the second term, this is theta, g r theta, it's going to be 0, d theta g r theta. So we've chosen mu and u such that this one survives. And well, what happens to these two?
Yeah, it's 0.
Both of them. Yes. Because this one is 0. Because gr theta is 0. Well, the same argument here, really. Oh, here's another version of super 0.
They also just are the same thing.
Yeah, they also cancel out. So even if they both have given us 4, they will also have cancelled out. So here's so this is very 0 together, yeah? By the way, this is not a general rule. It's not that if you look at this thing and you find one of them that is going to be non-zero by appropriate choice of mu and u, then the other ones are going to be 0. It could very well be that the other ones are also not 0. So it just happens that in our particular case, life is a little bit more simple. So the only one that survives is this one. And let's see what we get.
Are we forgetting a minus for all the half?
No.
No. No.
Oh no, maybe the minus somewhere else, never mind.
Yes. Okay, g theta theta upstairs. 1/r squared. Then take the derivative with respect to r of g theta theta downstairs, which is another r squared. Blah blah blah, 1/r. And that's also one of that I have on the list. Now this is how you do it.
How do we know that we're not missing combinations? Like, how do we know that that's it? Like,
Oh, there's
these
another
are all
one.
the good combinations.
No, no, this is not it. I mean,
Yeah.
this is two
With
examples.
with theta on top of the.
Yeah, I understand. There might be more mu's and u's that give non-zero. That's true.
Just to be careful with the way you think about this.
Yes.
Or try all 4 to them, which
Yes.
is kind of not very nice.
Yes. But you're right. I mean, what we've now done, we started by saying, how can we make this one non-zero? How should we choose mu and u to make that one non-zero? And this is how we found this one. Then we looked at how we're going to make this one non-zero. And then we got your option, that's this one. You can also ask yourself, okay,
Yeah.
how can I make this one non-zero?
Mu is theta and mu is r.
Yes.
And so it just switch them around.
Yeah, that's just switching around the mu and u.
Yeah, that's it then, right?
Yes. And so this one is also going to be non-zero, right? Because I've switched around mu's and u's, that means I'm going to check that this one is not 0. But I already know it's going to be give me 1/r. Why is that? Without doing the calculation. Sorry?
Because it's symmetric.
Because it's symmetric. Because from the definition you can tell if you switch mu and u around, you will get the same number. So you don't have to go through this whole calculation again for this combination, it will just give you the same. So you see there are all these little clever tricks to find out which ones work and which ones do not. Now when I was a student and was learning these things for the first time, I thought it was extremely elaborate. Sure, it's not as elaborate as doing all 40 of them, but it is still elaborate. And if you're not picking up this, don't worry about it, but at the end of the last lecture, I said that it's very analogous and
Analogous.
Thank you, analogous to classical mechanics, Lagrangians. Because what we found, to go from here to here, we found that things in space-time take the trajectory that gives them the least proper time. And in classical mechanics, Lagrangians, you have this thing called the action, which is the time integral of the Lagrangian. And that should also be such that it gives the least amount of time. So I knew that mathematics was the same. So I applied the Lagrangian technique, the mathematical technique on this case. And then you find a new formula that immediately gives you all the non-zero Christoffel symbols without going to this calculation. Yeah, I was very happy because I found, wow, look, it also works like this. And then I found that in some other books this was standard practice. But I felt a little bit proud that this standard practice is something I had thought of myself. One of the very few, well, let's not go there. I want to say one of the very few moments of pride in my studies. No, but that was really that I thought, well, okay, that means I see how things are connected now. So that's very nice. All right, this is how you go about. Now let's take the Christoffels that are over here as givens. So I'm going to erase this. And let's take all the non-zero Christoffels. Just go to calculating them all. Sure, go ahead. The non-zero Christoffels are these. There was one that I had wrong before. Which one was that?
That was r theta theta.
R theta theta.
Yeah, so that was this. That was
minus
minus
r
r
instead
instead
of
of
Yeah,
minus
okay.
1.
So R theta theta was minus R. Yeah. I'm just guessing here. Well, what I probably did was use the G theta theta upstairs where I should have used the downstairs one or something like that. That's probably one over the mistake.
Yeah, there's theta theta r, which is 1 over r.
Yeah.
That could be.
Just set things twice.
There you go. And the final one is these are ones. That's this step. We've now have the Christoffels.
Just a question, if in the exam the question is show that these Christoffels are non-zero, should we just do the calculation by hand and then in the end if we find the same result say that it is proven?
Well, I should formulate more carefully. What I should have asked is check that these Christoffels are correct.
Okay.
The way that I wrote it now is check that these are non-zero, but that sort of leaves ambiguous if you're supposed to then check if the other ones that I'm not listing are indeed zero. And that's a much more elaborate exercise. So my question would typically be, here's a couple of Christoffels, calculate of these that they are correct.
Okay.
3 of the 6 or something like that. Alright, next step. Curved space-time, well, it's not a curve, it's a Minkowski space-time in spherical coordinates. We have the Christoffels now. Let's go to the geodesic equations. What are the equations that how things move in this space-time? Now, one thing I can immediately tell, the time differential equation, where alpha corresponds to the time coordinate, is going to be extremely simple. Because there are no time Christoffel symbols. All the Christoffels with alpha corresponding to the time coordinate are going to be 0. So the time differential equation is just going to be this. That's this differential equation with alpha corresponding to time, and the Christoffels for all the alphas for time are 0. So you get this.
Sorry, the word 0 for which reason? Because you probably explained it, like I said before, I was taking notes, so
Sure.
slips.
But what's the question?
Why is the Christopher symbol for the time dimension equals 0?
Can somebody tell? Why? So your question is not how to get from here to here. That is clear, I think.
Yeah.
the question is, why are these with alpha equal time? Why are these 0?
Yeah, I think you explained the exercise before, but I was.
No, I did, but maybe somebody else can tell.
Because we take the derivative with respect to that variable of the entries of the matrix, and there is no t as a parameter in any term of the matrix, so that will end up as 0.
That's not the full reason though.
There's not-
because
no,
there's
there's-
also no non-zero. I mean, there's also no like non-constant terms in the R row column, and we do have results with R at the top.
Yeah.
No, that's true. I mean, just at one thing you say alpha is t corresponds to the time coordinate. Now you look at this expression, then you know beta is also has to be t, right? For the same reason as before. And then you know that this one is going to be 0, whatever, because you have to take a time derivative, and nothing in the metric had a time coordinate in it. So this is always going to be 0. And how about these? These might still be non-zero. Beta equals t, beta equals t. Why are these then still going to be 0? The argument that Lizzie gave just a second ago was, well, there's no time dependence in the matrix, so therefore time derivative is going to be 0, but it only explains you why this one is going to be 0. It does not explain yet why these are 0. There's a very quick argument why these are going to be 0 as well.
Yeah, I think mu and v have to be t as well.
Yes. Which is not a problem. I mean, beta is going to be t, yes? And we saw that the metric tensor only works if both indices, Greek indices are the same. So that means that mu has to be t. So I have gtt here. Why is that 0?
It's a constant.
It's a constant, it goes -1.
Yeah.
So that derivative is going to be 0. Here the same. In order for this thing itself not to be 0, mu has to be t. But that again is -1, of which the derivative is going to be 0. So, long story short, this one is 0 because there's no time derivatives in the whole thing. And these are 0 because these are going to be constants.
So they both need to be true.
For this particular question, it's not a general rule.
Yeah, in this case,
What did you
that's really like both
Why
need to hold.
Yes.
No t derivatives and
Christopher
no.
symbol for
Exactly.
time derivative was
non-constant
always
exactly.
was 0.
No, t derivative just tells you that this is 0. And the fact that everything in the t row and t column is a constant, it's either -1 or 0, means that these are 0. Long story short, yes.
What is the physical meaning behind this? That the t is always 0 for
Well,
Christopher symbol?
It's not always 0.
Just in this particular.
Just
Yes.
okay.
Yes.
So in this case, where we are like in a flat space,
Yes.
the Christopher symbol is always 0, which means that for that space.
Only in these coordinates. I can very easily come up with some even crappier coordinates for
Yeah.
which the time Christopher symbols are not 0.
Even for a flat space.
Yes.
Okay, just for this coordinate.
Again, it's
Okay.
not a general rule.
Okay.
So this means that there is no force acting on the
Yes.
time coordinates.
Exactly.
Okay.
Yeah, I mean, you do this and you're right, because what is a force on time? But then again, in general relativity, where space and time are entwined, if you have forces in space direction, you also have forces in time direction. You're not used to this in Newtonian physics, because in Newtonian physics, time and space are independent. And here they're not. So whatever happens to space might also happen to time. So there's a time force. It just happens to be 0 here. So that means that our time as a function of proper time is going to be what? It's an equation. It says this function, this time, is going to be a function of proper time, and the question is, what is its function, such that the second derivative is 0?
Constant
So
times
constant
tau.
times it, yeah.
Yeah, so constant times tau. If you want, you can also say plus another constant a.
Yeah.
But that's just,
Well, that's how you design your frame, right?
yes.
Yeah.
Or you can also call them boundary conditions or something like that.
Yeah. I have a question.
Yes.
Because you just mentioned the how space-time is one thing in relativity.
Yes.
Did we cover in the lecture why that is the case?
No. What I did was, originally I started out with special relativity, which I said there is this metric called the Minkowski metric, which has dx's, dy's, and dz's, and there's also dt now with an opposite minus sign.
Yeah.
And I put everything together. I never explained why that is.
Oh right, that's the starting point.
Yes.
So from the start, you kind of assumed already that.
Yes.
I think in the special relativity book we have seen a little bit of why that's true.
It's
And it was an alternate derivation of Minkowski, of the Minkowski line element, where that sort of like came in at some point.
Yeah, but I'm pretty sure that I know how Chris did that. He started out with saying light has to be invariant to speed of
Yeah,
light.
he did it the Einstein way.
Yes, and then dot 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 he finds the Minkowski metric.
Yeah.
And what I did, I started with the Minkowski metric, and I found that light is invariant for all. So there's no true real derivation. It's just which is going to be your starting point.
Yeah, I mean like the derivation more like shows why time has to be there as well. Right?
Oh, okay, sure. Yeah, I mean, okay, well, if that is the shortest way that I can say now, if you have assumed or found from experiment that things go with a invariant velocity, speed of light has to be the same for everybody, but if you're moving along with that thing, so the light takes less meters to move away from you compared to you because you're moving along with it, then time has to compensate in order to make the same amount of velocity come out. That is a answer. But it's really just a matter of starting. I hope you appreciate why my starting point is Minkowski metric and not speed of light being invariant. Apart from my usual rant about that I don't like thought experiments as a derivation of things because they come with messy experimental details. The real reason that I want to start with the Minkowski line element as my starting point for everything is because it's the line element, or if you will, the metric from which we derive everything here. So it's good to get used to this thing immediately. Okay, so that's one. What do you think this number is? It's a constant times tau.
It's going to be gamma?
It's going to be a gamma, yes. Well, we know this already because it's really Minkowski time in which we're playing around, for which we know that this relation exists, right? But just from a mathematical point of view, it could have been any constant, and it's up to us to decide later what that constant is. Okay, let's move on. We also have a differential equation for how things move in our direction. What is the strength, the force, if you will, with which something is moved along this line? That's what we're going to calculate now.
Can I just ask
Yes.
something? Well, when we find out that the scaling factor of tau would be gamma, can we from that assume
Yeah, I was
automatically
thinking
that
the
we're
same
in
thing.
Minkowski space?
Very carefully, I would say no. I'm sure you can find some. It's true if you have Minkowski metric that the relationship between t and tau is a gamma, but that's also hold the other way around. If you find that the relationship between t and tau is gamma, would that mean that you're in a Minkowski spacetime? That's a good question.
All toes are
Yeah, like all
the other way around.
all women have a nose, so that means that everybody who has a nose is a woman. I mean, it's this kind of reasoning, right? But it might be, but that for some mathematical reason that is the case. I don't know, I have to think about it. It's a good question. All right, let's do the R. Now you tell me what happens now. This equation, and I'm using alpha is the R coordinate.
Now you take all the crystals with R at the top.
Okay.
Yeah.
So what happens?
That's
I'll basically fill them into the geodesic equation there with the lambda and k.
Okay.
yeah. So you get
fill out the derivatives. And do it for every R crystal and sum them.
Okay. Well, tell me what the answer is. You're correct. It's just I want to know what the answer is.
Oh, me?
Or anyone really.
So yeah, because you were looking at him, but he was
I'm
like,
sorry,
no.
the group. I mean, please dictate what is going to be the terms that we're going to see here.
So first, let's take lambda and kappa as theta both, so we can get minus r times dx theta d tau d and yeah, squared basically. What's the other one? The other one is taking phi, so that would be minus r sine squared theta times d phi d tau squared.
Yeah, that's true.
So you can just add them. That's fine.
Yes.
Yeah.
Because
how it
no,
works.
this is what the notation
There's
means.
summation,
Right.
Yes.
Yeah.
You have to take lambda to have all
Yeah.
4 values and add everything together,
Yeah, of
adding
course.
everything together. You have to take
Yes.
kappa to be every value, adds everything together. Now the only ones for alpha r is when lambda and kappa are either both theta or both phi, and then add everything together. Now both of them being theta results in a minus r, well times the kappa lambda the x kappa, and we had lambda and kappa corresponding to the theta coordinate, so that gives you d theta d tau, and lambda and kappa could also both be phi, and then you get r phi gamma, which is minus r sine squared, which is this one. But because we have lambda kappa now both phi, gives you d phi d tau. So this is the differential equation that tells you how things move in theta direction. This is the force, if you will, that the part is, it's not truly a force, but I mean it corresponds to what in Newtonian mechanics would be a force. How strong particles, masses are moved along the theta direction. That's this function here.
Is there a reason why you didn't write it as the d theta d tau d theta d tau as as a square?
I wanted to be didactical. That's by writing in. I mean, of course, I could have written d tau d tau
Okay.
squared.
Yeah,
But I
I
wanted
thought you were going to use some sort of trick or something.
No, not at all. No, not at all. No,
Okay.
the only reason that I wrote it without the square
To
was
see it from
to
there,
see
yeah.
the correspondence.
At this point, the space looks curved, right? But it's not.
No, it
That's
does,
what's-
it does not. No, this
But
is.
it's from looking at this equation.
No, okay. Mathematically, you might, if somebody would come walk in right now, we haven't shown him the metric, and he would just look at this, he would probably say, wait a minute, something curvy is going on here. Right?
Why?
Well, because in
Wait a second.
non-curve in a curve space-time, you would typically have difficult expressions for these things.
Is it because there are like angles involved or?
Probably. It's the reason that we have these expressions,
Yeah.
these forces, if you will, is because we went to these coordinates.
Yeah.
And if you didn't know that we really start out from Minkowski metric, then this might suggest to you that you are in a curved space-time. You're not. This is Minkowski still.
How do you determine that again?
Well, I haven't really told you. One sort of suggestion is if you have these 4 equations and you solve them and you find that you're just looking at things that go in a straight line, then it might be Minkowski metric.
So the next step is solving this.
Solving
Okay.
this. This is one trick, but it's not a complete, truly full trick yet. There is there is another object called the Riemann tensor, big complicated thing, which itself is a combination of derivatives of Christoffel symbols. So it's big. It's to make it worse. It's a tensor, so with indices, but now with 4 Greek indices. So you can calculate how many options that thing has. Now that's a Riemann tensor. And the Riemann tensor, yeah, it's terrible. The Riemann tensor is a measure of if 2 things are moving in this space-time, if they close in on each other or not. If they do, then you're not in a Minkowski space-time, because Minkowski's things start out parallel, they stay parallel.
Yes.
And their intermediate distance to each other is given by another differential equation which has this Riemann tensor in it, which tells you how strongly they're closing in on each other or not. If that thing is 0, then it means no closing in, you're in a Minkowski space-time. So a real test is to see whether for a given metric you are in a curved space-time or an uncurved space-time but in really crappy coordinates, is to calculate the Riemann tensor. If it comes out 0, then you know, aha, it was a Minkowski all along. From this you cannot immediately tell, unfortunately. Yes, somebody had a... I thought there were questions, okay. Alright, let's quickly do the other ones, then have a break and then solve these equations, okay? Man, it's a long calculation just to find out that things move in a straight line. But we'll see. Very quickly, we also have some things moving in theta direction. Oh my god, I just made a mistake. Just a second ago I said this thing tells you how strongly things are being pulled in this direction. That was wrong.
Oh, it's in
Mhm.
that
Yeah.
direction.
It's in
Radial.
this direction. It's in the radial direction.
Mm-hmm.
The one that I'm writing down now is going to tell us how strongly things are moved along this line. What the force, if you will, is along the theta direction. Alright, you tell me what should come next. There's a practice in the notation.
Yeah.
No takers?
Wait.
Question is, what should come here? Equal 0, what should be there?
-1 over r.
Minus
plus
1 over r.
plus 1 over r.
Yeah, it's plus.
It's plus.
Plus 1 over r. D delta d tau d r d tau.
Yes.
One of the two.
Okay, there you go. Waiting for somebody to comment, but
Wrote 2 over.
aha. Yes. I wrote a 2, whereas the Christoffel symbol says should be a 1. Why do I write 2?
Because of symmetry.
To see if we're
probably?
still paying attention.
No, because of
No,
symmetry.
it's actually correct. I'm not.
Yeah.
Yes.
The theta r is going to be the same as the r theta
Yes.
Christoffel. So
Yes.
you actually have 2 of them.
Yes.
Mm.
If you look at this, if lambda is theta and gamma is r, you get this one then becomes 1 over r times d theta d tau d r d tau. That's one contribution. But if I would swap them around, this one has become r, this one has become theta, this would still be 1 over r. And this would just be the same product of derivatives, just in the other order. So they just combine and gives you 2 times that. What else?
Where they're both phi, so lambda kappa both phi. So it's minus sine theta cos theta
Theta.
d
Which one?
phi d tau d theta.
Yes. And because of
No,
lack of
2 over
space,
r.
it's right as a square now.
Yeah.
So there's that. Alright. Final one. Then a break, and then we're going to solve this. Now you tell me. I'm looking now at the force, if you will, along this line.
So it's 2 over r again.
Yes. And the 2 is obvious, yes? For the same reason as before. He was referring to this one. But swapping these numbers around would just give me the same Christoffel symbol again, the same 1 over r, so that it happens twice.
So there's actually another set of Christoffels which you didn't write.
Yes.
Okay.
Yeah, and that's common practice. That everybody in this field knows that if you write down r phi, you have also given phi r. Alright, so which derivatives are going to follow now? Because you can multiply with derivatives. Which ones are these?
So it's r. First one, no? Yeah. And phi.
Does it matter like with what comes first? Like if it's the or the
No.
doesn't matter since it's this one.
It's just a product. 4 times 3 is 3 times 4.
Yeah.
But that's not all, I think. There should be something else.
Where is it? Oh
No,
yeah,
cos
so it's
theta.
cos theta sine over sine theta. That one as well.
And
Plus
also with a 2. Right?
probably yeah.
Mm-hmm.
And this again indeed comes with 2. What are the derivatives?
D theta d phi.
There we are. 4 differential equations how something in this curved space-time will move such that the amount of proper time is the smallest. That's what we have written down now. We don't have the actual trajectory yet, we just have the equations that the trajectories obey. Nice. Alright. Before we solve this, is the notation getting clear now? How you work with these things? It is difficult, but it requires practice. And this is what I said before, it's a package deal. The other option would have been to write down all the 10 terms, 40 terms every time that I write down one of these equations. So it's the conservation of misery. Either I give you a notation that you get used to, that takes a while, but at least the equations look simple. Or I don't give you the notation and you don't have to struggle through the notation itself, but then the equations become horribly long. So something's got to give, and this is a convention. So just practice, practice. We have the 4 equations. Let's have a break, and then we'll go solve them, see if they give you a straight line.
Can I propose something? Since it's 5:32, why don't we finish X minutes earlier than however much the break is, and 10 minutes?
It's 5:32.
Really?
Yes.
Yeah.
We just put 40 minutes and.
Okay, you know that if everybody's okay with that, then we should do that.
Yeah,
okay, yeah, fine. All right.
Do you think
Man,
there's-
time
there-
flies.
Do you think there also still be time to do exercise B?
Yes,
Okay, nice.
because I think these are very easy to solve. They don't look easy, do they? Unfortunately. Take your timekeeping, Panos, because I find it hard to keep track of time.
Yeah, well, the same
Insert relativity jokes.
So like it's not
Same
like you have a
happened to us
watch
yesterday.
on your wrist.
Yeah, I got this a couple of days ago as a gift, so I am not used to having time around me all the time.
Yeah.
So, anyway.
So just
Yes.
question before switching. So those ones are the 4 equations that tell how an object that moves in straight lines has to go the fastest,
Let me rephrase.
the shortest path.
These are equations that if you solve them will tell you how something moves such that the proper time is the smallest. And when you said that you smuggled in the word straight line, the idea of general relativity is typically it's not a straight line anymore. This is what gravity does. In this particular case, it's going to be a straight line because I know it's secretly a Minkowski metric. But the general idea is geodesic equations, the solution gives you how things move such that the proper time is the smallest. Alright, man, complicated expressions. Well, this one is not, right? We have already solved it. The crappy thing about, let's say that we want to solve this one. Here's the crappy thing, in order to solve this one, that we know how things move in the r direction, in the radial direction, I need to take derivative of how it moves in the theta direction. So I need the theta direction in order to know what this is. I also need the phi direction. I already need to know how things move in phi direction to know what this is. So in order to find what r is, I need to already know what theta and phi are. Okay, well let's go to the theta differential equation. So we can get theta and get back to r. Well, let's go to the theta differential. Oh, that sucks.
Yeah.
Because this one requires r. So this equation tells you, well, I'm sorry, you can only solve me once you give me your theta. Then you go to the theta equation, tells you, I'm sorry, you can only solve me when you have r.
We've reached a stalemate.
Yeah, we have reached a stalemate, or how did we call last time? Chokehold. You cannot solve them separately. Crappy thing. Generally, in general relativity, the geodesic equations, you have to solve as is one big set of 4 equations. Which is much more difficult than solving each of them separately. We're lucky in this case that the t differential equation happened to be decoupled. We only have 3 equations that have to be solved simultaneously. The bad news is there is no general trick of doing this, solving these things. Coupled differential equations are very difficult, that's one thing. Second thing is there are so-called non-linear differential equations, because you don't just need the functions, you need the functions multiplied by one of the other functions. That makes it a nonlinear differential equation, and there's this rule in mathematics that says that there is no general scheme that you can follow to solve non-linear differential equations. That doesn't mean that the equations cannot be solved, it just means every time that you encounter such a set, you have to think of your own little trick for that particular case. There's no general trick that does it. So that sucks. Well, the phi, the same thing. If we want to solve the phi, we need to know what r is and phi itself. And we also need to know what theta is. They keep each other in this complete chokehold.
And even themselves, a little bit.
Yes, yes. This one needs itself. That's not an issue. That's by definition a differential equation.
Yeah.
Is that that they need each other in a nonlinear way is what makes it so difficult. What should we do?
I guess one way would be to rewrite one of the expressions just in terms of the first derivatives and then plug this whole expression that we get out of it into another differential equation to see if something cancels out.
Yeah, this was Freddy also mentioned a couple of days ago. He did. I think he mentioned that too. He said, "Well, take one of them and substitute it in the other, and hopefully something will cancel out of something."
Might be.
Yeah, no, that
would
works.
be my first idea because I
Sure, that works. That typically tends to work or clean up a little bit. Not always. Sometimes it does. So yeah, one thing that we could do, say, is you know what? Let's take another derivative of this one. Now, why the earth would I take another derivative? I already have two derivatives here. Make it more complicated. Make it a third derivative. But there's a reason, because taking the derivative of this thing gives me ultimately a second derivative of theta in there, right? Via product rules. And then the second derivative of theta I can use this one for and substitute it back in. And hopefully I can make something that is theta independent. Sometimes it works, sometimes it does not. So, but yeah, it's an option. You can tell this is going to be a mess, yes. Another derivative, in order to get the second derivative of theta, so I can plug this one in. But what I get back via the product rules is even more terms. It's a crappy situation. Here's a trick, one that is very often used to solve these things. Well, let me give you two tricks. One of them is make a very clever guess. 5. Okay, 5 works actually, because if you take all of them constants, phi is a constant, theta is a constant, t is a constant, then this is all just derivatives, so everything will be 0 equals 0. So a particular position, no motion at all, is indeed a solution.
Well done.
So that's good. Well, that is a clever guess. Yeah.
I knew it. Can I get my PhD now?
No.
That always be a solution to every kind of geodesic equation.
Yes, because geodesic equations are always derivatives. So a non-moving thing is always an option. There is always a solution.
The non-moving thing will not really tell you anything about
How is
shortest paths.
Yes.
Well, shortest path for shortest proper time.
Yes.
Right.
But in principle, it's true. That's always the solution. But
Kind of trivial, yeah.
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 So yeah.
They don't teach these things in differential equations.
And no, they
No.
probably don't teach you nonlinear differential equations, right? They're probably all linear. I'm guessing.
Yeah.
I think we did solve some non-linear, but
Yeah.
we solved like a special cases.
Yeah, well, there is no general rule for nonlinear differential equations, and fortunately, physics, the laws of physics, almost all of them are linear, inherently linear. It's only when well, not only there's other cases, but it's a hallmark of relativity that the equations are nonlinear. It's not even the case. It's not because of the situation that we happen to be looking at. Look, we have the simplest situation, Minkowski space-time, and it already comes out nonlinear. Okay, I wanted to say there's 2 tricks that people typically use. One of them is a clever guessing. Another one is by symmetries. And by symmetries I mean, well, just from your starting point to what your space-time is, maybe you can sort of already guess what the solution should be. Not entirely, but at least what properties you should have. That limits your options. I will give you an example in a second. Let's do the first option, namely clever guessing. We already solved this one, right? Because it happened to be a decoupled differential equation, we saw, well, the time is a constant times proper time. good question before was, doesn't this already tell you that it should be Minkowski space-time? I'm not sure if that really holds water. That really works, right? Everybody has a nose, a woman has a nose, so everybody has a nose is a woman, that sort of thing. It's true for Minkowski time, this is what you get out. I'm not sure it works the other way around. But it is a clever guess. I mean, it sort of gives you a suggestion, maybe it's secretly just Minkowski time. And in the Minkowski time, you know that things go in a straight line. So what you could do now is, well, I'm just going to guess that it's going to be a straight line because I have a hint here that it might be. Take a straight line, put it in and see if it works. If it does, there you go, problem solved. That's one option. Here's the second option. Symmetries. Suppose that I go back to my situation here. Look at the sphere. One very nice thing about spheres is that they look the same in all directions. Doesn't matter what your value of theta is, it will always look the same. Agreed? Okay, so if the thing will give me the same answers for any theta whatsoever, why not choose my theta in a way that that makes life simple? Do you see that argument? Let me repeat. We were looking at a sphere. And the nice thing about spheres is that they look the same in all directions. Doesn't matter how you look at the sphere. It's a perfect sphere. It will look the same regardless of what your value of theta is. So it should give me the same physics back regardless of my value of theta. I have a freedom in choosing my theta. Because it's going to come out the same anyway. That's a symmetry. So that means I have a freedom to choose my theta. Why don't I just choose my theta properly? What would be a good choice for my theta? Given that I'm allowed to choose any theta anyway.
You could probably choose it such that d theta comes out as 0.
Well, that means that we're going to take a constant theta. That works. We're free to choose our thetas. Let's take a constant theta. That means that this one will drop out. And this will drop out. This will drop out. So we've already cleaned up. Maybe we can make it better. We've chosen a constant theta.
You can make it 1 or 0, because then the part of the sine and cosine is going to be 0.
Yes, but which is a clever choice? I mean, we have chosen theta to be a constant. We have that freedom. We've chosen it as a constant, so therefore a lot of these terms drop out. We've only used that it is a constant. Now, which constant are we going to use to make it even simpler?
I would use it as pi over 2. No, 0, because then you could just drop out the last term and the upper.
Yes.
Yeah.
Well, there's two options here. You can say, you know what, I want to get rid of this whole thing. And one way of doing it is saying, well, I'm going to make my theta 0, because then the sine of 0 is going to be 0, and this drops out. And this drops out too. That will make life simple. Not the best choice though. And that's for a mathematical reason. Look at this thing.
Hey.
Cancelled it out.
Then we
You
divide
already
this.
cancelled it out.
No, that's not how it works.
No,
No, I agree with that. You say, well, I've already chosen as a constant, so this one drops out. Mo, be careful now. Because we've chosen theta to be a constant means that this is 0. But if I take my theta to be 0, then that means it's infinity. 0 times infinity is undetermined.
Always a fun problem to solve.
So we still need to keep track of what we've done before.
It's not in the order. Even if you've first chosen theta to be 0, and then have chosen it to be constant, it will run up against the same problem. The problem is in the indeterminacy of 0 times infinity. So mathematically it's not allowed. So which other would you do?
Pi over 2.
Pi over 2. You would have the same effect, because with pi over 2 as your choice, it's going to be the cosine that's going to be 0. Agreed? That's good news. The sine is not 0, it's going to be 1, but this whole thing will be 0.
Yeah.
So you know what, let's choose theta as pi over 2. It means this whole thing drops out. This one still drops out with no mathematical difficulty, because then you have 0 over 1 times 0, which is perfectly allowed. How about this?
This one.
That's fine. So by this appropriate choice, this symmetry trick, we've reduced our differential equations to something much more simple.
Could you have also like try and get a value for phi instead of
Yes,
theta?
you could also do that.
Okay.
It's the same symmetry because what we've now done is use the fact that if you look at the sphere from this side or from this side, is the same for any theta. It also works
And
from
then-
this. So you could also have done the same with the phis. What else? What is this differential equation now, by the way?
It's just
So d theta
something that won't give you something linear anyway, right?
is 0.
It's just a second derivative is equal to 0.
Yes, but it's the second derivative of the thing that's
Oh, yeah.
pi over 2. So this one just gives you 0 is 0. Well, that's correct. So that's one is solved.
Never heard that before.
And then the final one that we have is d phi d tau squared plus 2 over r dr d tau d phi d tau. There you go. How about this? We've simplified it enormously now. Just by using the fact that the thing should look the same for whatever value of theta.
Still coupled though.
It's still coupled, that's true. But I think that this substituting one in the other is going to be much more easy now.
Yeah.
But let's be even more clever.
It's another symmetry you can make use of, right?
Sure. We've now
In
used
phi.
that the phi, that the sphere looks the same for every theta, it also looks the same for every phi.
Yeah.
So which phi we're going to choose? Well, it doesn't really matter,
No,
does it?
it's
It's
just
any
any.
phi, right? Just a constant phi.
Yeah.
So we're going to use the same symmetry but now in phi direction. So which one cancel out? This one you get rid of? Agreed? This whole thing you get rid of? By the way, this then is 0 again. So what we now have are two differential equations that are automatically solved. 0 equals 0, which is correct, both of them. This one gives you the r, second derivative of r equals 0. What should r be?
No, it's something times r. That's times 1. You just have.
There you go. Is that a straight line?
Yeah.
Something is moving along this line with constant velocity.
Yeah.
There you go.
So we did hook that.
Yes, we did.
Nice.
Do you agree? This is a symmetry trick.
But
Symmetry.
what if it was not symmetric?
Life would be much more difficult. Now, it's not my choice that is symmetric, it's the space-time itself with which I started that was symmetric.
Yeah, but you knew it was symmetric. Yeah, but you were starting just from that.
Yes,
You didn't know it was symmetric.
that's true. Yes. No, you're right.
So what?
Then you have to do another trick.
Are you gonna tell us this?
No, no, I'm not teasing you here. It's really, there is no general trick. So if you tell me what if it was another space-time you cannot use this trick, I cannot tell you, well, for other space-times you have to do this. You have to first tell what the space-time is, and then we have to divide on the spot what the trick for that one is. There's no general trick. It's always starting afresh with every new space-time that you start with. Unfortunately.
Fortunately, peanut butter.
Alright, well,
Fortunately, peanut butter.
so this is exercise C. Finally, there was a question, let's do exercise D.
Yeah.
We have now found motion. By the way, we have found that things move in a straight line constant velocity. It's not quite the same as saying that you're in Minkowski spacetime. Because in order to have that, you have to have two things and see if they close in on each other. It's what you need this Riemann tensor for. But it's a very strong suggestion that it is, yes? Alright. Exercise D was every motion in a curved spacetime should obey this law that let's apologize myself here, but I think I made a minor mistake in when I wrote the exercise. I think I said should equal to c squared, it's minus c squared, but that's a minor issue. Every motion in a space-time should always obey this rule. Let's see if it does. This should be true always. It's a direct result of the line element. Well, let's see if it's true. For our motion that we found, let's first write this out. What is u0? The motion in time direction. This by definition is dx0 d tau. So what is that thing? dx0 is time, yes?
Yeah,
It's just a
Constant.
constant that is
It's a constant.
time.
Yes.
Yeah.
So we don't know what the constant is?
It's gamma.
Yeah, we know. Suppose you didn't know. Okay, if you started from here, you cannot be certain that it is a gamma. So let's call it something else. In fact, let's call it. I want to call it G, as in possibly gamma. But before we know, let's call it with the lit. But the G already has so many other meanings in relativity.
You go for K.
Go for the
Constant.
Russian G.
Yes,
Russian
with the Russian
G.
letters again.
Is there such thing as a Russian G? I have no idea. It's called K. Unknown number.
Okay.
Okay. By the way, we also have an unknown number here. We also need a letter for
Russian
that.
G
Which
is-
one is that?
Is it?
An L.
Sorry? An L, sure. Okay. Alright. So what is u0, which by definition is dx0 dt, which by definition is dt d tau? What is that number?
Well, K.
That's K. We don't know what the number is, but it's K. How about u1? And u1 in r coordinates is the r coordinate. So that's dx1 d tau. dx1 is dr d tau, because the 1 corresponds to the r here. What is this thing?
L.
This is called L. Agreed. Let's move on. ut, which by definition is do xt d tau, and the xt was what we called the theta here. What is this?
Well, that's 0.
That is 0. Because we chose our theta to be constant, pi over 2. And for the same reason, u3, which is the x3 d tau, which is the phi 3 d tau, again equals 0. Right, because we were looking at a constant phi. Okay. Let's write out this contraction. You tell me, what should I write? Let's put the metric back up because we're going to need it for the contraction. The metric was -1, 1, r squared sine theta squared. There's a contraction. You have to have alpha get all values, get beta have all values, and that add everything together. This is 16 terms in total.
It's only going to give non-zero when alpha is beta.
Yes, I only give you the non-zero when alpha is beta. This is because this diagonal thing here. Well, that means that it's going to be G00
Yep.
TT GTT times UT squared. Right? And what else?
It's the same for RR.
And there in principle is also theta theta and phi phi.
Yeah, 0.
Well, they're not themselves 0. The G
Yeah.
theta theta and G phi phi are not 0, but they're going to be multiplied by 0, so might as well not write them down. So this is all there is. Equals minus c squared. Let's put in what we know. GTT, what is that number?
1.
Minus 1.
Minus 1. UT, what is that thing?
K.
Yes, so that gives you k squared.
But is it not minus the minus, so it should be 1.
Why is it minus?
I was just asking, like normally there's always a minus before the tensor.
Yeah, but on the other side it's minus c squared.
Oh, it's at the.
Yeah.
Oh, okay. You know what I mean?
The thing that the way this is written here is now correct.
Oh, okay. I thought that we forgot the minus
Yeah,
before.
but the minus is at the other side. It's at the
Oh,
minus c
okay.
squared.
Okay.
What is GR? That is 1. So that gives you UR, which is L squared. I have no idea why I wrote an L here. Should be 2. Huh. Oh, does this help?
Doesn't look like it.
No, we have an unknown number K. We also have an unknown number L. And if you square them and subtract them from each other, you should get minus C squared. So X and L could still be any numbers, right? There's always a combination of X and K's and L's that makes it work. So, yes.
Isn't that kind of like Pythagoras theorem as well?
Yeah, but with a minus sign.
Yeah, if we take c to okay, no.
Well, this is not really helping, is it?
Nope.
How about this? Let's work on the L thing. dRd tau. This is correct. It's correct, but we can do better. dRd tau is the same as dt. Agreed?
Yeah.
Times dt dr. dt d tau. Make sure that you understand why this is true. It's not relativity, this is just mathematics. It's a chain rule, differentiation. And don't we know what dt d tau is?
We don't. That's coming.
No, we don't know. Otherwise, we wouldn't do it.
Sorry.
No.
Otherwise,
It's a
all the
number.
things
It's
will
a-
be
yeah.
meaningless.
So we already gave that thing a name, dt d tau.
Okay.
Okay.
That is k.
Oh, that's velocity.
And this is a velocity. It's the velocity with which somebody is moving along this line. It's a velocity in r direction. It's the amount of meters in r direction divided by the amount of time as seen by that guy. It's just a velocity that somebody sees somebody move along the r direction. So we might as well call this v. It's literally the velocity with which you see somebody move along this r line.
That would be three-dimensional velocity, so to say, right?
In this, yes, but remember that we chose our theta as such that it is along that.
Yeah, okay.
But yes, in principle it's a three-dimensional velocity. Let's go back here. So what we called L, excuse me, what we call, was it L? Yeah, what we called L before is really V times K.
Mm-hmm.
I see beautiful things happening here. Because we were looking at what K was, right? Alright, let's do this like this. Minus. Am I a minus missing?
I think so.
There's something wrong
There's something.
Between
It's minus
should
1
be
plus.
v squared minus 1.
It's plus v.
in between brackets.
Yeah.
There should be a minus.
Yeah.
Or that, yeah.
So that means that you get c 1 over v squared square root. Does that look gamma to you right now?
A little bit, but
Yeah.
Shouldn't c also be squared?
Yeah, there's a c.
Okay, then you can just like divide both sides of the fraction by c squared now. So the top is 1, and
Yeah.
the bottom then become. Oh wait a second.
Yeah. I see. Okay. Well, no, this should be a gamma, and it's close to a gamma, right? I mean, it's 1 over 1 minus v squared and then square root. You know, here's my stupid thing. You know that I think in c equals 1 units, right? I forgot to put a c in here somewhere at this part. Can you see where?
but dt.
So the dt part.
It should have been c
C
times
dt,
t. So there's an extra c here.
So one
So it's
over
correct.
there.
So that means that this should have been with another c squared, right? Because u0 is k times c. That's the one that should be here, so it gives you another c squared. That means that there is a c squared here, and this is c squared over there. I'm just correcting my c mistake. Right? I forgot x0 isn't t, it's c times t.
Yeah.
And in my mind, c is always 1, so I forgot to write it down. I'm just correcting the mistake, no new physics, just algebra, and that will give you this. Which is indeed gamma.
That's what I said in the beginning.
Yeah, we knew this from the beginning, but only because we knew that we
just
started
kidding.
with the
But
Minkowski
wait,
space.
hang on. So, but that's not what we're proving, right? We were proving that the contraction is equal to minus c squared.
Yes, what I did was, how should you have chosen k in order to make it work?
Oh.
And then you find it should have been gamma. And then you know, wait a minute, it wasn't Minkowski Swiss time all along because things go in a straight line.
Yeah.
And
You knew it, man.
yes, you knew this. But again, this is an exercise in practicing notation and going through Christoffel symbols and such. So we haven't learned anything today. The only thing what we've done was something we already knew in new notation. You can imagine next week what we're going to do. Oh, we have to talk about the exam. Yes. Just as where we are content-wise, what we've done now is taken our series of steps and applied it to Minkowski space-time just in our coordinates. Something that looks curved. From next week onwards, we'll actually apply to things that are curved. And then no straight lines anymore. I can promise you that, and no demos.